Hello, welcome back to es346 Basic Thermodynamics. This is module 4.4, Specific Heat Temperature Effects. And the section in here is actually 4.4. That's a typo. Alright, here are the three learning objectives for this module. At the end of the module, you'll understand the molecular basis for the temperature dependence of Cp and Cv. You'll be able to calculate an average specific heat value, and you will also be able to calculate a high precision specific heat value via integration. So, previous module we talked about the specific heat, and we had Cp values and Cv values, and we used them to calculate changes in delta H and changes in delta U. Well, that turns out that the heat capacity is not constant over temperature. And so on the plot here, this is a plot of Cp as a function of temperature. And you realize that for some materials, like the noble gases, Cp is more or less constant. But for other molecules, there's actually a temperature dependence, and the heat capacity goes up. The reason for that, if you remember what we're talking about when we talk about internal energy, we're talking about molecular motion. And when we have something like a noble gas, the only molecular motion we have is translation. And so as we add more energy, the molecule tends to translate more, which is reflected in temperature. However, when I have a more complicated molecule, anything with a bond, O2 or H2O, I can now get these other modes like molecular rotation. I can go ahead and get molecular vibration. Therefore, in order to get it to translate faster, I have to put some energy in to also make it rotate faster and vibrate faster. It's a quantum mechanical aspect of it. So therefore, it looks like the heat capacity increases with temperature. And that's what we're seeing in these types of plots. So when we have processes with large temperature changes, we need to account for this dependence on temperature of heat capacity. Now, this I'm showing is table A2B, and this is the heat capacity, but now it's for materials over a range of temperatures. So up on the upper left here, we have the heat capacity for air over temperatures in Kelvin from 250 to 1000 degrees. And the first column is Cp, and the next column is Cv. And again, I want to also point out, Cp values are always greater than Cv values. And this table, A2B, has it for various materials. We have air, carbon dioxide, carbon monoxide, hydrogen, nitrogen, and oxygen. And something else I want to point out is the range that Cp changes with temperature. So, for example, let's just go down and look at the hydrogen value. At 250, my hydrogen value is 9.9. At 1000 degrees, so in order of, well, increased it fourfold, I've only increased to 10.8. So it's only increased about 10%. Well, the hydrogen molecule is fairly simple. It's just an HH bond. However, if I look at carbon dioxide, at 250 degrees, it's 0.6. However, at 1000, it's 1, so it increases about 60% over that same range. And that's because it's a more complicated molecule. It has a bending mode, which the hydrogen doesn't, and it has an extra vibrational mode. So as the molecule gets more complicated, you'll have a larger temperature dependence with temperature, a larger temperature dependence on heat capacity. Now, one other interesting aspect, though, is that the heat capacity is independent of pressure. And this was actually done in a famous experiment by Joule, the same person that the unit's named after, in 1843, so it was a long time ago. And what he was looking at was to find out, does the pressure affect this value we see, that we know it now as the heat capacity? So what he did in this experiment is he had a tank, and he insulated it very, very well, and it was full of water. And inside that tank, he had a tank of air and then a valve, and then he evacuated the other side. And he let this come to thermal equilibrium and measured what the temperature was with a thermometer. And then he went ahead and opened the valve and allowed the air to expand and double in volume. And so in essence what he was doing, let's think about this, is this was like having a piston cylinder with some little stops to keep it when it's pressurized, then removing the stops and allowing the system to expand, which is doing some boundary work. However, since it's doing it against vacuum, the boundary work was equal to 0. So our first law energy balance, which is delta U, is equal to, well, the energy that goes in, it's completely insulated at 0. minus the work that it does. And in this case, the boundary work was 0 because it was against a vacuum. And so there was no change in internal energy. So if there was no change in internal energy, the other thing he noticed is there was no change in temperature, but there was a change in pressure. So that means that the internal energy is a function of temperature, but not of pressure, which means that this value CV, which is du dt, is also not a function of pressure. So therefore, when you look at tables of the heat capacity, they'll be a function of temperature, but not of pressure. Now, I should point out, this is true only for ideal gases. Once you have a real gas, the heat capacity would be a function of pressure. However, in this case, we can just go ahead and find our values of U from the table, and we don't need to use the heat capacity value anyway. All right, well, before we do the next example, I want to provide a little bit of context of why this might matter. And so what I'm going to show here is just a quick schematic of what's called carbon capture and sequestration, or CCS. And this is a process that's been invented recently in light of global warming and the increase in CO2 concentration. And one of the main generators of CO2 is power plants. And so the idea was, well, after the power plant generates that carbon dioxide, instead of just releasing to the atmosphere, can we capture it and sequester it? Now, in order to capture it, the first thing we need to do is take the flue gas that is mainly a mixture of carbon dioxide and nitrogen and remove the carbon dioxide from the nitrogen. And in order to do that, the first thing we do is it's cooled down and then it's run through an amine solution, which is just a solvent for CO2, but not for nitrogen. And so then you end up with getting N2 released in that exhaust, and then the carbon dioxide is absorbed in the amine. Then you run it through a reverse process where you then release the carbon dioxide from the amine. You now have no nitrogen, and you can have pure CO2 that you then go ahead and sequester. And it's often sequestered in like old mines or old oil wells, such as this. But the important process where our example comes in is the first thing we need to do is we need to cool the CO2. And it's coming out fairly high from a power plant, 500 to 1,000 degrees, and we need to get it down to about room temperature. So here's the example related to that. We have carbon dioxide, and we have to cool it from 500 degrees Celsius to 25 degrees Celsius after combustion. And we're going to do that at constant pressure. And what we want to know is, what's the cooling requirement per kilogram of carbon dioxide? So let's go ahead and think of it as it's a constant pressure system. So this is a lot like our piston cylinder device. We're cooling it, so we're moving heat Q this way. And if it's constant pressure, there could be some boundary work done on the system. And we want to know our answer, Q per kilogram of CO2. So we can imagine our mass in here is just 1 kilogram of CO2. And we want to find Q. So let's write our first law energy balance for the system. Change in internal energy, delta U, is equal to the energy that goes in. Here we have boundary work going in. It's going to be compressed as it's cooled. And then minus the heat, which is what we're trying to solve for, which is Q. Okay? Now, a little bit of kind of intuition here when we look at this. If we're removing heat from a gas, it's going to contract. That's why we know that the volume decreases, and that's why that we could think of this as a positive boundary work going in. So let's return to our equation over here. We have M delta U, and that's equal to the boundary work at constant pressure. So that's going to end up being P. And for a positive value of boundary work, that would be V1 minus V2, because the initial volume is greater than the final volume, minus Q. And I'm going to use, we've got carbon dioxide here acting as an ideal gas under these conditions, so I can go ahead and make this mCv T2 minus T1 is equal to P V2 minus V1 minus V2 minus Q. And since this is a constant pressure process, again, I can move that work term over here to make this an enthalpy. This will be mCp T2 minus T1 is equal to minus Q. And now we can go ahead and plug in our numbers, and we've actually got the temperatures. So we're doing this per mass, so that's just equal to 1 kilogram. We need the heat capacity of carbon dioxide. Well, it starts at 500 and goes to 25. So what we need to do here is find an average value. So I'm going to find an average value of Cp. I'm going to make it Cp at 500 plus Cp at 25. And take that, the average value. So we'll go to table A2B and look at my values of the heat capacity. And so I'll find out that that heat capacity value is about 1.035. So that's what I'm going to go ahead and put in for here. So let's go ahead and calculate our Q now. So our Q is going to be equal to the heat capacity of 1.035. And then my change in temperature, so I'll flip the sign here. So this is now going to be 500 minus 25. And that's going to give me my cooling requirement of 491 kilojoules, and that's per kilogram of CO2. Now, using that average value works okay if our temperature changes aren't really large, because effectively what we're doing was we said we'll take a value at a low temperature, take a value at a high temperature, draw a straight line through it, and we're going to go ahead and approximate it as that. Well, looking at this, for some materials, that's actually going to introduce maybe some amount of air. It may actually be some considerable amount of air. Now, this only occurs when I have really large temperature changes. Look at the range of this, 1,000, 2,000 degrees. So I'm changing 500 to 1,000 or 2,000 degrees. That would matter. And you might wonder, well, who deals with temperature changes that are that large? Well, NASA's really interested in that, and they were very interested in it when they were designing the space shuttle, because the space shuttle is coming in pretty fast. In fact, it's coming in at around 5,000 miles per hour when it comes into the entryway. And all of that kinetic energy is turned into thermal energy, and you can kind of see it from this thermal image that you see on the diagram here. And there were huge temperature changes in temperature, and they wanted to be able to know what that temperature would be in order to design the space shuttle. So they couldn't use this average value to get real precise. And so we needed to go ahead and come up with a model that would pick up all the curvature of these lines that you see here. So again, this is sort of where in engineering we throw up our hands and say we're just going to get an empirical model. And this is a common empirical model used for the heat capacity as a function of temperature. We have Cp is A is a constant, B is a constant, as is C and D, and then T is temperature. And usually temperature is an absolute in these equations. And so for each individual material have different values of A, B, C, and D, and because of the nonlinear terms, we're able to pick up the curvature that you see here. Now, one other small subtlety I want to mention, but that is important, is you see this value here has an overbar on it on the line. And that's because these units for Cp are often something like kilojoules per kilomole Kelvin, so instead of kilogram. And so we actually would need to go ahead and convert using the molecular weight to get from Cp with a bar to the value that we're used to using in engineering for mass. And we'll see that in an upcoming example. So first I want to show where you get these values. So now we're at table A2C. So we're moving through table A2 with heat capacity. And now what we have is the constants A, B, C, and D that go into the equation. And so I have the equation. It's kind of small written up there, so I rewrote it down here. And again, remember, this is per mass. So this is going to be, now we've got this in English. So this one is actually BTUs per pound mole degree Rankine as my value of Cp. And if I wanted to change that, what I'm going to do is I'm going to divide that by the molecular weight to get it per mass. So look at the values we've got. So for example, if we were using carbon dioxide right here, we have 5.316, that's the value of A, and then 0.793 times 10 to the minus 2 for B, etc. They give you a temperature range that they're valid, and you realize they're valid for very large. There's about 2,500 degree temperature range that it used. And the air, if you look, is all less than about 1%. So they're very, very accurate representations of the heat capacity to temperature. Okay, let's go ahead and do an example here. So for example, we were NASA and we wanted to go ahead and create some of this hot gas to test our panels on the space shuttle. And so what we needed to do was we needed to heat some carbon dioxide from 40 degrees Fahrenheit to 2,500 degrees Fahrenheit, several thousand degrees. And we were going to do that by putting an electrical heater into there, and we want to know how much energy it's going to take to go ahead and generate that. So here's what our system is. We're going to look at how much energy it takes to heat 2 pound masses of carbon dioxide. We're going to go from 40 to 2,500 degrees. So if we look at our system here, we've got electrical work coming in, and if this is at constant pressure, there's going to be a boundary work term out. So right, our first of all, energy balance. Delta U is the energy that goes in, and that right there is going to be that electrical work that we're trying to calculate, minus the boundary work, WB. And again, recognize that this boundary work, it's at constant pressure, so this is WE, the electrical work, minus P, and I'm going to have V2 minus V1, and I can combine that PV term with delta U to give myself delta H is going to be equal to the electrical work, and delta H is going to be M, and the integral of Cp dt, because Cp is a function of temperature, so in order to find the differential change, I'm going to have to go ahead and do that integral. So let's go ahead and remember Cp, I'll write that equation again. Cp is equal to A plus Bt plus Ct squared plus Dt cubed. And we need to do that integral. So now we're going to have that our electrical work is equal to the mass times, and now we're going to have to do this integral. So we're going to have to integrate Cp. So the integral of Cp is going to be At. Integrate the next term, B over 2t squared plus C over 3 t cubed plus E over 4 t to the fourth. Right? And we're going to go ahead and need to evaluate that from 40 degrees to 2500. And recall these were an absolute temperature, so we need to add 460 to get from Fahrenheit to Rankine on each one of those. Okay, so that's going to go ahead and give me my electrical work. So let's go ahead and put some numbers in here. This is going to be kind of a long equation, but sort of straightforward. So there's my 2-pound mass, and now my value of A. And so what I'm going to need to do is go ahead and get the value of A. So, I showed it here. Let me go ahead and erase some of this stuff. So you can see those values. Okay. All right, so here's from the table A2C, and my value of A is 5.316, and then I'm going to multiply that by my temperature change, so that's going to be 2960 minus 500, so that's T2 minus T1, this is that term there, plus 1/2. My value of B is 0.7936 times 10 to the minus 2. And then my temperature change is 2960 squared minus 500 squared. All right. Now I'm going to need to, C is negative, so I'm going to do minus there. This will be 0.2581 times 10 to the minus 5. And temperature again, 2960. This is cubed minus 500 cubed. And one last term, D, so plus, this is over 3, and D is over 4, so 1/4 of D, that's 0.3059 times 10 to the minus 9, and 2960 to the 4th minus 500 to the 4th. Okay, pretty long, messy equation there. And if I want to go ahead and actually determine what this energy is in terms of BTU, then I have to divide all of that by the molecular weight. The molecular weight of CO2, which is 44 pound mass per pound mole. All right, so a lot of algebra in there, but we'll go ahead and calculate that in, and we can find out what our value of the electrical work is. And the electrical work is 1387. And that's going to be BTUs. So a lot of algebra goes into this, and they're kind of messy, but they're really easy to do, particularly if you put them into a spreadsheet. All right, there's one last concept I want to mention between CP and CV. And all of these things, recall, we've been looking at ideal gases. And that's the only time we're going to use CP and CV, because that way CP and CV are only functions of temperature. Once it's a function of pressure, it's easier just to look them up in tables like the steam table. Now recall that CV was equal to du dt. That's actually what the definition of it is. So I can actually rewrite that as du is equal to CV dt. And I can do the same thing for CP, where dH is equal to CP dt. Right. Now recall that the definition of H is U plus PV. And so PV for an ideal gas is equal to RT. So this is also equal to U plus RT. And if I were to then go ahead and take a differential of this, I would have that dH is equal to, over here, du plus d dt of RT. Well, that's simply equal to du plus R, and that over there is dH. And so what I realize is the difference between dH and du is this value of R, and so Cp is equal to Cv plus R. So anytime you want to go ahead and get Cv values from Cp, you would just say that Cv is equal to Cp minus R. So recall from table A2C, it only gave you values for Cp, but you can always get Cv by just subtracting the value of R.